from Seoul National University, and we'll talk about the Cartan geometry of the rotating Kepler problem.
Yes, thank you very much, and thank you for the invitation to Princeton. It's nice to be here. So basically what I'm going to talk about are computation of Koenig-Zehnder indices. And so maybe I should first start for why you want to compute them, because I assume that you're not entirely familiar with them. So the idea is compute indices. And so what are they good for? So let me first give an example of why they can be useful. So this is a very primitive example which I came up with myself, so it's kind of, this is not realistic. So the idea is you want to construct a global surface of section using finite energy foliations, and these indices have something to do with that. So here's the example. So construct global surface of section. At least that's the first idea. For, well, let's say a very simple setup. So we have S3 with its standard contact form. So we don't actually care what contact form is. We need to know that the flow is given by, flow has this form. So it's very, very simple. Everything is periodic. And you should think of this as just the double cover of the geodesic flow on S2. So what's this? So double cover of geodesic flow on S2. And so, well, so what's the idea using these holomorphic curve techniques? So in general, Hofer, Wysotsky, Zehnder, holomorphic curve techniques. But maybe I just mentioned this very simple example. So what we want is we want a family of holomorphic curves, say holomorphic planes, that foliate R times S3. Or if we want to look at the three-body problem as R times RP3, or R times, well, this connected sum of two copies of RP3. And so it's a nice fact that this this symplectic manifold is isomorphic to just C2 minus the origin. And you're very lucky with this particular flow that if I take the standard complex structure here, it is actually a symplectization complex structure. So then you can say, well, let's just take this. This is a holomorphic function. And it's asymptotic to one periodic orbit. Just look for large z. If z becomes very large, then it just goes to this one periodic orbit in the first factor. Yes, after projecting, sorry. Yeah, or asymptotic. Well, okay, yeah, well. Okay. So now, okay, so you project to get here, to get foliation. So on S3, you get something like the following picture. So this is supposed to, the blackboard is supposed to represent S3, so we put in an additional S1 symmetry. So this is this one periodic orbit. And you have a bunch of planes going through them. And, well, I don't know, this is a very standard picture. And what the point is that the rape flow is transverse to that. So, okay, so this is the simplest situation. And if you want to put this in a context of the three-body problem, it would be, well, if you're optimistic, just the Kepler problem, and then it would be something like, well, some spanning orbit for some disk spanning orbit in the Kepler problem. So okay, so what has this to do with these indices? Well, in general, we need to look at these holomorphic curves. So what holomorphic curves can there be? So in general, consider more general holomorphic curves, so maybe not planes, but maybe more complicated objects. So we consider, say, some map from a punctured sphere also into, well, R times, in general, maybe some other manifold. and so asymptotic to these periodic orbits. Okay, and so what's the point now? You can collect the solutions. Oh, so maybe I should say they should satisfy some equation. So they should be. Should be J-holomorphic, so they should satisfy some PD, and so collect them into a moduli space. So this will be a bit. I won't give any precise definition. Well, okay, so I give some additional data. Say R times M. So, okay, so these are just solutions of this problem. Maybe I call this star. Up to reparameterization. So we have one example. So just the example, the earlier example was just M gamma, which was this simple orbit, and no orbits downstairs, and just in S3. But in general, well, many things can happen. I don't know, I just draw some pictures. So, and here should be the gamma plus orbits, and here should be the gamma minus orbits. Okay? And so now, if you're lucky, or if you have some transversality, then this M can be thought of as a manifold. So given some transversality conditions, M is a smooth manifold of dimension equal to, well, a bunch of numbers that depend purely on the orbits, and these are exactly these Koenig-Zehnder indices. So let me write them. Well, say hi. And there's some correction factor, which I'm sure to get wrong now. So let me. And it should be -1. Yeah. 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 I've dropped out the genus to make it easier. So let's just check for. It should be for index 3. It should give 2. So if I put in 3, and then here 1 positive puncture. Well, I think it's it's wrong. Well, maybe it's like this. Okay. Well, okay. So the main point is that you can say, given some transversality conditions, you can tell what the dimension of this manifold should be. Okay. And if you check the correct formula, which maybe this isn't, then you see that the previous example that I gave comes in a 2-dimensional family, and the Koenig-Zehnder index is also equal to 3. So toy example. Toy example is actually a bit cheating, but so use this Koenig-Zehnder index is equal to 3, and it corresponds to a 2-dimensional family, and that's enough for foliation. So maybe this may be important to point out that if the index is too low, then you can already, for that reason, not see that there cannot be a foliation, which with maybe just some one spanning orbit. So now I can talk. When I talk, I can now choose what direction I go more. So the main point of this talk will be how to compute these indices, or well, one way to compute these indices. I can say a little bit more of why I want to have a dynamically convex. That means index larger or equal than 3. Should I draw the picture? Should I say this? Okay. Okay. So what's the idea? So below the Lagrange point, and if the mass of the moon is sufficiently small, maybe very small, very light moon, then this picture is approximately correct. But as you go over the Lagrange point, it's certainly not correct. So what happens for, so now h larger than h Lagrange points, so then we get, as Urs described, a connected sum of RP3. Well, say alpha, alpha free body, I don't know how to. So I write it like this. So on one you get the moon contact form, and the other you get the Earth contact form. But okay. And so what's the picture then? The picture is pictures that you know. On what blackboard can I write? I cannot write here, right? Okay. Let's just. So the picture is you get this neck that develops, and you get this halo or tube orbit there. So what happens? So connected sum, and so you get this picture. And so here is one RP3, and here's another RP3. And so here, well, so I have to cheat with dimensions, but what? So here you have some index 3 orbit. So okay, so this is actually some computation. So this is what we actually did the last week. What's happening? Okay. So exists for small mu. But this is just direct computation, nothing intelligent. Then here there's you have this neck for the connected sum, and inside this neck you have this halo orbit, as it's called in this business, or Lyapunov orbit, and this has index 2. And at this point I suddenly realized that I haven't defined an index. I just said it's some 2 to compute this. Maybe I should say a little bit more. Yeah, I can say it late, but I now realize that I need it at some point, some not real definition, but at least fake definition. So, okay, I'll wait then. Okay, so what happens now is, so near this orbit, it almost looks like that. So you get some family of disks, and it starts to run. But now here, what happens is, near this orbit, it starts to, this family of cylinders, of planes goes there, and then it breaks up into a cylinder, and then, well, there's a plane here and there's a plane here. So family breaks. So there's a clearer picture of that. And this is a very standard picture. So it's this picture. So again, you need to use this rotation symmetry. So here you have an index 3 orbit, and here you have an index 2 orbit. And so what I'm saying is that you have this family of disks, and that starts to break here into a cylinder and a disk. And on the other side, you have also a family of disks which does the same kind of. Okay. So now you see kind of, if there are index 2 orbits, then this foliation doesn't behave that nicely. It still behaves, but it's not as nice as this. So what we want to do is we want to see that at least near the heavy body, there are no index 2 orbits.
Maybe at this point we point out that since the surface is all transversal to the flow, they already, if you stay in this region, really force you to go around.
Oh yes, it is. Sorry.
Unless you exit.
Yeah, so the flow is always transverse. So yeah, that's the that's the point. Yes, so the ray flow is always transverse to these things.
So for example, the neck entering this part has to be also transverse to the foliation, so it's being automatically forced to go out. And of course, if it stays too long in there, the tube cannot start intersecting itself and it runs because of the uniqueness of the initial anymore. So you fill up volume, but there's only a finite amount of volume. So at some point, some of the stuff has to go back out. And that means precisely when you intersect the stable manifold. Just for a picture.
Yes.
Now
Yes. Okay. So then I want to draw one more picture. Kind of. So what's kind of the scenario that we want to exclude with this computation is the following. So suppose that we have here this RP3 with, say, alpha Earth, and then we do a connected sum with RP3 alpha Moon or something. So now what could happen, so we know, well, if the Moon is very light, then maybe much lighter than it actually is, then we know that there's some index 3 orbit. So that's this one. So that's, maybe I should say, this is this retrograde orbit. This corresponds to this retrograde orbit in the rotating Kepler problem. So in the rotating Kepler problem, you put mu equal to 0, and then it's just the Kepler problem in rotating coordinates. And the circular orbits there in the Kepler problem will still be periodic orbits in the rotating Kepler problem, just with period will a bit change. And so one of them is closer to the Earth, and that has index 3, at least for small mass. Now, what could happen is that if there's another index 2 orbit, so here's one, this halo orbit, but if there's another one, the foliation might already break up here. I don't know whether this is good or bad. It's interesting if it exists, but it's good to know whether it exists. Okay, so the point of this talk will be...
But the foliation will be thin.
Yes.
Other stuff coming from the other side.
Sure.
The complete foliation of the space.
Yeah, so presumably you have done...
Except you have, when you come there with your tube from the Lagrange orbit, then you have other things standing in the way. And if you go above, the tube, part of the tube goes above, shoots in that direction, the other part shoots down there. And so then you get a really, it explains the distribution of this hyperbolic orbits coming from that tube. But one would have to be able to, in order to get a precise picture, one has to compute it.
Okay, so this was basically the introduction, why I want to compute indices. And so how do you compute an index? So should I postpone giving a definition? I can postpone. Maybe I give some fake definition. So you should think of the index as kind of, you take a periodic orbit, so you want to compute the index of an orbit. You take the periodic orbit and you linearize the flow near to it, and then, well, you should think of an index as a kind of winding number of this linearized flow. So this is not a definition, but it's good enough for the talk, basically. So if it rotates, so first of all, it needs to rotate in the right direction. If it rotates in the wrong direction, then maybe the indices become negative, and this would be not so good. So they need to rotate in the right direction, and they need to rotate fast enough. So you need to investigate the linearized flow. But if I say it like that, then the only thing seems to be find all periodic orbits and linearize the flow, and that's, well, for the three-body problem would be undoable. So here's another approach. So compute or estimate maybe estimate indices without computing linearized flow, or actually without computing any periodic orbit. So I'll start with a bunch of definitions. So the idea is that if your Hamiltonian describes, say, the geodesic flow on a manifold, then actually the indices must be positive, or well, for other reasons. So the idea sometimes CZ index is Morse index of a certain action functional, of energy function, of some energy functional, so maybe say geodesic flow. So this is the initial idea. So we want to think. So first, well, we were of course interested in the three-body problem, but this is a bit complicated. So first, we shall look at mu is 0, and well, if you look at it, well, you don't see that much. But I want to argue that you can interpret this as a Finsler metric. And so let me first give the definition. Definition. So a function from the tangent bundle to the non-negative numbers is Finsler if the following three conditions hold. So first of all, so this should be continuous. Let me continuous function. And we say it's Finsler if the following three conditions hold. So first of all, on the complement of the zero section, it's smooth. It's a smooth positive function. And secondly, you have some scaling homogeneity property. So what you have is the following, which we require, is that if we fix a base point, so this is in M, and we fix some vector, and we take, say, lambda times a vector, then we want this to scale, well, not linearly, but say just positively homogeneous. So meaning the following, we can pull out the factor lambda if lambda is positive. Well, or not, well, zero is also okay. And finally, you can compute the following thing, just take the square of this. So you think of this as a kind of norm, but it's a kind of failed norm because I'm not asking that a vector that's plus a vector has the same length as minus a vector. But now you can take the square, and what we require is that if we take the partial derivatives in both fiber directions, this should be positive definite. In other words, it should be like a Riemannian metric. So if you're familiar with this term, in each tangent space you get a Minkowski metric. I'm confused now. So let me give some examples. So the first obvious example is just to say, well, just take a Riemannian question. Okay. So the first example is just to say, well, we can take just a Riemannian manifold and just take its norm, and that works, of course. So mg Riemannian, and then you can just say f xv. Just define this to be, well, and then if you, well, everything works, of course, and of course, what you do this, if you take the last recipe, then you get just the Riemannian metric back. Okay, and so now a little bit more interesting example. So mg Riemannian, say alpha some 1 form. Then what we can do, we can kind of make a more honest Finsler metric. So it's a kind of norm. And so by doing this, so the 1 from alpha should be small enough for that. So this is not reversible. So what happens is that minus a vector is not the same as x of a vector. Well, as long as alpha is not 0. Okay? Yes. So now, okay, so actually, to be honest, I should actually say that, well, maybe first a picture. So a picture would be, if I look in the, so this is a picture of the unit, unit tangent bundle with respect to f. So if f is actually Riemannian, then it would just be some nice round circle if we look at a Finsler surface, or in general just a sphere or ellipsoid, so symmetric around 0. And so an honest Finsler structure would look more like this. Well, okay, the second derivative should still be nice enough, so you have to interpret the picture in the right way. And okay, so now the first thing that I should say is that the Hamiltonian is a function of the cotangent bundle. So actually, I will not be working with Finsler metrics, but rather with Cartan metrics. So, well, this is not, I don't say definition. So there is a dual notion on T star M, and that's called Cartan metric. But you copy the definitions. Just write stars. And okay. So now, the first thing that we want to verify is that, so Urs showed last Wednesday that, so Wednesday, Urs showed that this alpha, say, RP3 and an alpha 3 body is star-shaped. Well, okay, so he showed it even also a little bit above the first Lagrange point. So, but in particular, below the first Lagrange point. So now we'll ask the question, is it fiber-wise convex, which is basically this Finsler. So claim, or it is fiber-wise convex, so i.e. Finsler.
But this, that if you go to the double covering and you can view it as there's a coordinate change which presents it as a.
No, I mean that.
So where's the fiber?
I mean, as fiber, I mean it's a unit. So RP3 is just the unit bundle of T star S2, and I can kind of I will show you a recipe that kind of using the Hamiltonian I cook up a Cartan metric on T star S2.
So you describe sort of a conjugated system as on the cotangent bundle of the two sphere, but as a system.
Yes.
Okay.
Yes, and then it's from that description it's obvious that well, from the picture is that the radial vector field, which is Liouville, is obviously transverse to this thing. Yes. Okay, so that's that. Okay, so as I said, first we do it for we do it for mu is 0, because there will be some disappointing result, which kind of prevented us from doing it from mu larger than 0. So if we put mu equal to 0, we get the Hamiltonian for the rotating Kepler problem, and that's the following. So, okay, and so maybe, should I say something about critical points of this? So there is this critical level, the first Lagrange point if you want. So so the value of the first Lagrange point is -3/2, but it's not, you don't have an there's a whole S1 symmetry, so you don't have an isolated critical point, but you have a whole family of critical points. Okay, so this is a kind of degenerate member of the family, but it's a good thing because you can compute here most things. Okay, so then the next one. Okay, so what we now do is we fix an energy level of this Hamiltonian. Let me see that there. Yes, and then we fix an energy level of this Hamiltonian. So consider and so then we regularize. So we define K as this rotating Kepler Hamiltonian plus C, and then we do this Moser regularization by multiplying with Q. And so what we get is something nice. And you see already some things appearing. So you get K is 1/2 P squared plus 2C times Q plus Q1 P2 minus Q2 P1 times Q. Okay, so now we want to say if we take a point, so remember in Moser regularization P, Q, so this is a point in S2 and this is a fiber. So this is Moser regularization. And so we want to say what's the length of such a vector, right? So, so the length of, we want to say what's the length of this one, length. And so how do you do that? Well, in general, Q does not lie on the, this point will not lie on the hypersurface. So I should find a scalar, I should scale back the fiber vector such that they come on the surface. So I find, so find lambda such that, sorry, K, yes. Yeah, okay, so now you can solve lambda, and that should be the length of this vector. So I won't do the computation and just give you the answer. And then declare that this is Cartan. So F PQ is, so it's dangerous to do formulas by heart, but it is certainly this form. Okay, so this is the nice part, and now comes the not so nice part. Q1 P2 minus Q2 P1 divided by the length of Q, and then P squared plus 2C, and if I remember correctly, it was squared here. Well, so okay, you can solve, the point is you can solve it explicitly. I just want you to observe that you have this funny term here, and notice that if I multiply Q with some lambda, this one doesn't scale, because here it's linear in lambda and here also, or not linear, one homogeneous. And so this determines basically the most part of the length, but this kind of gives us the shift. So this is a non-reversible metric. Non-reversible, but not standard. So in Finster geometry there are lots of types, but this is apparently not one of these types. This is apparently a new type, or some old type in very good disguise. Maybe I should point out that if you forget about this term, then this would be just the co-metric in stereographic coordinates for a sphere of some funny radius depending on C. Okay? So the claim is that this is, now I should say this is joint work. Always forget this, joint with Kai Cieliebak and Urs Frauenfelder. And so the first claim is that this thing is Cartan, PQ is Cartan, And so this implies, so this is a corollary, the indices are so indices of every geodesic is non-negative. And so I should also point out that geodesic, so it's still extremal of length functional. So if you have such a Finsler metric, you can define a length, well, basically because you have a norm, although kind of this direction is different, but you can still define a length, and geodesics are still solutions to our original problem. Okay, so now what's the point? The point is now we want more than this, right? We want to have the indices not just non-negative. We want them to be larger or equal than 3. So how do we get that? Well, there are additional things. Namely, if you look at the round sphere, then the curvature forces indices to have a certain behavior. So maybe I should say a little bit about that. So I think I can write here now. Okay, so, well, so how much curvature do you want to hear? I can just give you a theorem, and if you're happy with that, maybe I first give you the theorem and explain a little bit. Yes, okay, I just give you the theorem. So notions such as curvature and also geodesics, as I just pointed out, such as curvature, can still be defined. So at this point, it's important to point out that these GIJs they form a family of Riemannian metrics in the fiber. So if I fix a point in the cotangent non-zero cotangent vector, then I get a metric from there, and then I can, well, just pretend that there's no problem, that actually this thing varies, and then just try to use the same formulas. So then that doesn't work really out, but you can correct for that, and well, it's hopefully that suffices. So this gives rise to Christoffel symbols. And so you can get a connection from that. It's more complicated than the Riemannian setup, but you can make some choice that everything works. Okay, so now the theorem that will help us, and so this is due to Harris and Paternine. And so what's the statement? So the statement, if the curvature is large enough and geodesics are also long enough, then everything is good. So what's the precise statement? So suppose that F is a Finsler metric on, what's this? I think it works on anything. So say S2, and the curvature, so this is the Gauss curvature. So the formulas are more complicated, but if you insert the Riemannian metric, you just get the same result. So suppose that the Gauss curvature is positive, and the length of the shortest geodesic so you have to have some bound, pi divided by, I need to look this up, square root delta. Then what is it? so the, maybe I should say, then the unit tangent bundle, so the set of points, I should, and the unit tangent bundle is dynamically convex, meaning all indices of contractible orbits are larger or equal than 3. Not in this theorem. So you have a stronger theorem where that constant shows up. This is just a weak theorem.
This is not quite sharp. So.
No, you can do better than this. But the next theorem kind of tells us that there's no point. Okay, so CZ gamma contractible larger or equal than 3. Okay. So maybe I should briefly say the idea for this. Something about the idea for this theorem. So the idea here is to is the following: if you have a Finsler metric, then so if you have a Finsler surface, maybe I should say, so it's a surface with a Finsler metric, then there is a canonical framing, or we should really say co-framing. So you have 3 one-forms that trivialize the cotangent bundle. And okay, so they have some nice relations, but maybe I should point out that the first one is actually the contact form. Or, well, it depends how you order them, but this is how Harris and Paternine order them. And so now you can take a dual frame. It will be x1, x2, and x3. And they're nice in the sense that this x1 describes the dynamics. So that's the rape field if you want. And x2 and x3 trivialize the contact structure. That's the kernel of this one form. So you have a kind of natural candidate for your linearization. Since it's globally defined, so you don't need to care about does this trivialization extend over a disk. It will extend over a disk. And so now the idea is to say linearize the flow along geodesic gamma. So things are, maybe I should also point out that before I do that, there is a natural complex structure by just sending x2 to x3. And so given that setup, you can write down the linearized equations, and they're very nice. So linearized flow. So I write, so you get a path of matrices that transports these vector x2 and x3. So the derivative of this path is given by J times the following matrix. So J is complex structure, so it looks like this. And this is the Gauss curvature. Okay?
But that depends a little bit on, just from what you said, x2 and x3 are not at all unique, right?
No, well, there's a canonical co-framing.
Yeah, whatever that means, right? So canonical, so you choose them basically so that you get that form, right?
Well, okay, if you want, yes.
Yeah, in that sense,
Yes,
okay.
yes. Okay, so now the point here is that this always rotates in the same, so if k is, so the worst thing that can happen is k negative, then it doesn't rotate. And if k is positive, then it rotates in the right direction. And now if geodesics are long enough, you will always make it to Konitsen x equal to 3. So the idea is always rotate in the right direction. So long geodesics. Imply we make it. Or if you like this crossing description, maybe I'm the only one who likes the crossing description of Konitzer index. I would say the crossing form of this one is always, well, it's always signature at least 0, and if it's positive, if curvature is positive, these crossings form contributes 2. So then you also make it. Okay, so then we are very happy. So now we want to show something about the curvature. So I can show you many formulas. I don't know whether you want this. Then I need to turn on my computer. But I can also give you the short version. The curvature will become negative for the rotating Kepler problem. So this is not the way to...
We don't make it.
Yes, you make it, but not all the way. So I can show you pictures. So maybe theorem, well, also with the same people. So the rotating Kepler, so this metric for the rotating Kepler problem has negative curvature so we fix the energy level equal to minus c. So if c is, now I have to, if c is smaller than, so okay, so the idea is that the Lagrange point is at minus 3/2, and then at this minus 165 about, I mean, it doesn't really matter at this point anymore, it becomes negative. And here it stops being a Finsler metric, and the curvature does very nasty things. Below, it's kind of very nice. So a long time we were hoping that we got positive curvature because we're mainly looking at, well, some energy level well below the Lagrange point, and then it looked okay. But this is not the way you're going to get dynamically convex. Yes?
But the point where it becomes negative is very far outside.
What does it mean?
Yeah, so...
It's close to the zero velocity curve.
Yeah, so, well, I can show you the pictures later if you want. So where does it happen? So for the radial, so for p coordinates, so it depends where it becomes negative, what energy level you take. So if you go all the way to the Lagrange point, it's about for p. So the curvature looks, okay, maybe I should draw some very rough picture. So the curvature is a function on the unit cotangent bundle, but the Kepler problem is S1 symmetric, so it kind of, you can cut it down to a function S1 symmetry, a function on S2, and so okay, so this is P, and this coordinate, let's call it phi, so every fiber is an S1, so let's parameterize an S1 by just cosine phi, sine phi. If you do that, the picture looks roughly like something like this. There's a bump, which is here, and then here it becomes negative, and then it increases. So if you look at for large p values, it looks completely harmless. And then for p, so this is about for p is 1. But it depends on the in which direction you're looking. So, well, okay. So I think that's all I can say without turning on my computer.
Where's the Lagrange point? If you're really close to minus 3/2, then you almost see the Lagrange point. Where's in that picture?
This picture, if you go really close to the Lagrange point, okay, I'll give 2 pictures. Okay, so first maybe C is 2, so that's far away from the Lagrange point. Then curvature is positive and does something like this. Now we do, so the last one was this.
Yeah.
I think it looks something like, so this is minus 40 and this is something like 40. But I mean, you can get any number you want.
What are this graph is what?
This is P, and this is, so I inserted so I just inserted a fixed direction, and then you can just compute it along an axis.
Somewhere on that, you have to see the Lagrange point, right? It's not quite, the critical point is not there yet, of course, but
No.
it's almost critical, right?
Oh.
Where do we see that on
No, I think I won't. No, I will have to look up. So here it starts to change very rapidly. It's kind of
I sort of would expect that it happens.
probably the Lagrange point is here because it's actually, if I change and say opposite to the Lagrange point, then so I guess the Lagrange point is actually here, where the curvature does.
In words, what's the statement now?
The statement is what statement do you want?
Yeah, well, so the curvature becomes negative for energies
Above,
sufficiently
yes,
high, but still below the
Lagrange point.
Going up to the Lagrange points, it gets sort of worse and worse and worse.
Yes, yes. Well, it is not even a metric anymore at the Lagrange point, so it's
Yes,
to be expected.
So that means there are regions. This is hyperbolicity. What does that mean, actually?
Yeah.
What are the dynamic consequences of
Yeah. So
curvature?
So there's this interpretation of positive curvature means geodesics bunched together, but I mean, if you ask more,
For Riemann metrics, I think that's solved. Right?
Yes.
Then they bunch together. If negative, they would sort of try to
Yes.
diverge.
So then
But how is it with this? Is it the same intuition? This kind of
there is a similar intuition, but if you want me to say more, I have to read more.
But does one see that on the rotating Kepler problem? What that mean? I mean, is there something? I mean,
Near that point.
do you see divergence of certain things?
Yeah, I tried numerically some things to see what these orbits do there. Yeah, I can give you a kind of description what happens near the Lagrange point. So you have some orbits going in some direction, which they are harmless, and the other they try to go. Okay, so you have this rotating frame, and there are orbits that are kind of a little bit faster than your rotating frame. But at the Lagrange point, your rotating frame is as fast as your orbit. So basically you're standing still, that's your critical point. So near your Lagrange point, what happens is you're a little bit faster, but not fast enough, so you make a kind of funny turn. So your orbits seem to be very slow, and then they twist. So well, if that helps you.
Not yet.
Yeah, well, so something, I mean, okay, so if you say, if you were looking for hyperbolic orbits, then this would be a good candidate to look here, I guess, which is near the Lagrange point, by the way. But
So do you have any chance to check the pinching condition for these for negative energies? I mean, sufficiently.
yeah, so the thing
The
is,
statement was sort of unfair because you have to also know the shortest geodesic, right? Not unfair, the Harris pattern. So you need to do two things.
yeah, okay. So you can, yes.
Yeah,
So
it's true for different reasons, but can you check the condition?
For very far down, you're closer to the flow.
yes.
Yeah, but yeah, I know that, but that's not for different reasons. But if you want to actually apply Harris pattern line, you need to know two things.
Yes.
Curvature
No,
and the shortest geodesic.
No, okay, so there's a stronger version where you can basically directly apply the results of Rademacher improved this a little bit. And so then you need to know the pinching factor.
Well, improve this one.
Yes, but I prefer to give this one because this was easy to give an explanation why this holds. And if I just wanted to make the easiest result where you can see, well, this means something. So I think you can, yes, I think you can, so you want to make a statement about, you want to have some condition on the curvature and conclude something about dynamic convex, right? That's what you're asking?
I was just asking, can you ever verify Harris pattern line?
No, not in the way I phrased it. Well, I mean, for the rotating Kepler problem, you can certainly do that because you can just, well, you can parameterize everything if you want. But that's kind of cheating. You make you can make a bunch of coordinate changes, and at least in principle, you can just solve everything. But that's not. So the point of this approach is to say that this in principle works for mu, for any mu. I don't care what mu is. In principle, you can just do this computation. But then, okay, so then you have a valid point that then we need to check some other things.
But you don't know that for any mu you have principal metric, do you?
No, we haven't checked this, but this looks kind of, well, it's not easy, but it looked doable when we started doing this. I mean, now it kind of, the point is kind of, do we want to do this? Well, we can try to do it, but there's less reason to do so, because you cannot conclude anything about this. So maybe I should also point out that actually we have, you can just, in that situation, you can directly, so if for the rotating Kepler problem, you can directly compute the indices. So you can just bypass the theorem, and then you are dynamically convex below the Lagrange point. But
give the good news.
yes, so there is good news, but this method is not going to do it.
To prove that it's dynamically convex.
Yes.
So that means, despite the fact that you have this negativity of the curvature, which could screw everything up, the fact it runs presumably sufficiently fast through it, then it doesn't matter.
Yes. Yeah. So you
Back a little bit, but not.
well, you spend some time there. Well, the point is of this that you never rotate back. You always rotate in the right direction. You can just, if you have negative curvature, you're standing, you're not rotating. But if you spend enough time in the positive regions, then you will have large index.
So then the other proof says that is precisely what happens.
Yes.
It's sufficiently amount of time
Yes.
in the rotating
Yes.
region.
Okay. So you get again for free that the index is positive.
Yes, you see this directly. Yeah, you see it. I think you see it very nicely.
I'm just a little bit confused.
Yeah, sorry.
Yeah, well, so it's so I think what is mu is small, in some sense sufficiently. And if you go to the real Kepler problem, presumably you see some of the features there.
Yes. Yes.
Small, and then presumably you can also have some interpretation of the curvature and so on.
Yes.
And curvature negative would say that it's regions of hyperbolicity and so on. And what that says, where the other method presumably Konicina is still greater equals 3, just means you are in these regions of hyperbolicity, but you have to be quite often also in some other parts, because otherwise it would
Yes.
that the other result would be worse.
So it's really interesting. So you do this for the rotating Kepler problem,
Yes.
and then get the curvatures, and then
Yes.
you conclude then from mu sufficiently small,
Yes.
like he was saying, you get
That
a lot of features of that.
that was the initial idea, but the initial idea was even that this approach doesn't care about mu. So if you just compute long enough, then maybe you can even do this for any mu. But well, I mean, we are now less willing to do this computation since we already know in advance that the result isn't going to give us dynamically convex. So, well, okay, so it's kind of
But nevertheless, what you see in the
Yes.
rotating Kepler problem transports over
yes.
to nearby.
Yes,
A lot of
yes.
this- lot of features.
Yeah. Okay. So I guess I should finish here, or I have already finished, I think.